When you unlock your phone with just your face, or get a perfect instant answer from a chatbot, it feels like pure magic, right? Well, it's not magic, it's math. And today, we're going to pull back the curtain and find the one calculation, the real secret engine that powers all of it. So let's just ask it straight up. What's the number one, most important calculation that makes all of modern AI even possible? I mean, think about it. Every single neural network, from the tiny ones to those huge, large language models, what's the one fundamental thing they're all doing over and over and over again? And the answer, well, it's almost ridiculously simple. It's just multiplication. Seriously. But hold on, we are not talking about your third grade times tables here. We're talking about multiplying these enormous grids of numbers billions upon billions of times every single second. That one operation, that's the secret engine we've been looking for. All right, so this superstar operation actually has a name. It's time to head down into the engine room of AI and meet the star of our show, GEMM. GEMM. It stands for General Matrix Multiply. And it's basically a standardized way of multiplying two matrices, those grids of numbers we just mentioned, as absolutely fast as humanly, or I guess siliconely possible. Don't think of it as just one brick in the wall. No. It's the entire foundation that the whole cathedral of AI is built on. Okay, so when engineers are working on GEM, what's the end game? What are they trying to achieve? Well, it boils down to these four things. Speed, obviously. Faster is better. Throughput, which is all about cramming as much data through the system as possible. Efficiency, because you've got to save power and money, especially at a massive scale. And finally, scalability. You want this stuff to work on your phone, right? Not just on some monster computer in a data center. So how in the world do you take a simple multiplication problem and make it run at light speed? Well, that's where we get to the really good stuff, the secret sauce. This is where a bunch of super clever optimization tricks come into play, and they are the key to unlocking everything AI can do. We're going to look at three key techniques. They are parallelism, blocking, which is also called tiling, and vectorization. Each one is a genius trick to squeeze every single drop of performance out of the hardware. Let's break them down. First up, parallelism. Okay, imagine you have 1,000 math problems to solve. You could have one person do them one after another. Or you could have 1,000 people solve one problem each, all at the exact same time. That's what a GPU does. It has thousands of little cores that are like that team of 1,000 workers, all crunching numbers simultaneously. It's just massive. Next, we've got blocking, or you'll also hear it called tiling. The best way to think about it is like this. Picture a chef cooking a complex meal. It would be crazy if they had to run to a giant walk-in freezer down the hall for every single spice, right? So inefficient. Instead, a smart chef preps everything first, putting all the ingredients in little bowls right next to the stove. That's blocking. It breaks the huge math problem into small tiles and puts them in the processor's super fast nearby memory, called the cache. Much, much smarter. And the last trick is vectorization. This is like a processor superpower. Instead of telling the chip, hey, multiply 2 times 3, and then, okay, now multiply 4 times 5, a vector command is like shouting, hey, multiply all of these 8 pairs of numbers right now, all at once. It's a bulk order and it saves a ton of time. Okay, so we've got all these tricks to make things go fast. But this brings up a huge dilemma, a question that every AI developer wrestles with. What's more important, speed or perfect accuracy? Because, and this is the interesting part, you often can't have both. This all comes down to a trade-off in precision. The best way to think about it is like a photo. You can have a giant, super high-resolution photo. We'll call that FP32. It's perfect, every detail is there, but it's a huge file and it's slow to load. Or you could have a smaller, slightly compressed version, like an FP16 or an INT8. It loads way faster, takes up less space, but you might lose a tiny, tiny bit of detail. So the big question for AI is, can it still figure out what's in the picture, even if it's a little blurry, if it means getting the answer 1,000 times faster? Okay, I know, we've been getting pretty deep in the technical weeds here, so let's zoom back out. Why does any of this matter to you? Well, because all these little tricks have a huge, direct impact on the tech you use every single day. Let's talk about the real-world payoff. You can see the whole chain reaction right here. It all starts with making GEM faster. That leads to faster calculations overall. That lets developers build way bigger and more complex AI models, like the LLMs that power chatbots. And that is what gives us the incredible apps that feel like magic. It's a straight line from optimizing one math problem all the way to the phone in your pocket. And the benefits for all of us are super real. For the big tech companies, yeah, they save a ton of money on their cloud server bills, but for you and me, it means that AI on our phones is instant, not laggy. It means data centers use less energy, which is better for the planet. And maybe most importantly, it makes powerful AI accessible to more people because it can run on cheaper devices, not just on multi-million-dollar supercomputers. When you boil it all down, it comes down to this: milliseconds. That's the whole game. The difference between an app that feels slow and clunky and one that feels instant, like magic, is whether it can do these billions of multiplications in the blink of an eye. That's what optimizing GEMM gives us. It's the engine that makes things happen now. But of course, the story isn't over. Not by a long shot. This stuff is incredibly hard, and engineers are always bumping up against the fundamental limits of physics and hardware. So let's take a quick look at the challenges that lie ahead. Yeah, there are some really big hurdles. For one, you've got hardware dependency. You might write this amazing, super fast code for one brand of chip, and it's completely useless on another. Then there's that precision risk we talked about. Going faster is great until the AI starts making dumb mistakes. There are also these things called memory bottlenecks. More on that in a sec. And honestly, this is just mind-bendingly complex code to write. It's a huge challenge for even the smartest people in the world. And this quote right here, it just nails that memory bottleneck problem. It says, no matter how fast the multiplication is, the system cannot improve if the memory cannot send data fast enough. It's like having a Formula One engine, but you're trying to fuel it through a tiny coffee straw. It doesn't matter how fast the engine could go, if the processor is just sitting there waiting for data, all that brilliant optimization we talked about is completely wasted. So that leaves us with one last big question to chew on. As we keep building more and more powerful AI, what's going to be the thing that pushes us forward? Will it be brand new, fundamentally smarter algorithms? Or will the next giant leap forward come from just getting better and faster at doing this one simple thing: multiplication? The race is definitely on.